Hello, and welcome to a precipitation type forecasting training module on the top-down approach. In this module, we hope to review the top-down approach, the science involved, and also give you a little bit of application to the probability of weather type, and also some techniques in the operational environment. My name is Dan Baumgart. I'm the Science and Operations Officer at the National Weather Service in La Crosse, Wisconsin. Let's get started. The top-down approach, as many people know, has three important layers: the ice-producing layer, the warm layer or hydrometeor altering environment in the mid-levels typically, and the surface cold layer. Let's start by looking at the ice-producing layer. When we look at the published research of over 15 observational studies, ice nucleation occurs in the -8 to -17 degree range. So as temperature decreases, the probability of ice introduction increases. What we're talking about is a layer that has a saturated layer that has no ice currently within that layer. So we're looking at a cloud layer at -7 here, has approximately a less than 10% chance of having ice introduced just initiated within that cloud layer. But as temperatures decrease, you start to see the probability that ice will nucleate in that layer increase. So temperature is decreasing and the probability of ice introduction is increasing. Once you get to about -12, you have about a 70% chance of ice nucleation within that layer and the conversion from supercooled liquid over to ice. By the time you get to -15 Celsius, about a 90% chance of ice introduction occurs within that layer. So when we bring it back to the forecast environment, temperatures for saturated layers that are warmer than -5 Celsius, depicted here, have a very remote chance of having ice introduction. So these layers should be diagnosed as supercooled liquid layers. Looking further aloft at the cold air temperatures of -10 to -20, you see that there's no saturation and therefore there's no ice present in this environment. As we move back to the probability of weather type, the probability of weather type uses a prob ice present grid in GFE. This prob ice present grid is calculated by looking at relative humidity values of greater than 75% with respect to ice in that -8 to -15 important range. And the probability curve can be seen over here on the right. So the temperature in the layer is diagnosed on the bottom of this graphic, and the probability of ice present is seen on the left. So the values here run up the right-hand side column of the graphic. But as temperature decreases, you can see that our probability of ice is really increasing. So this is the curve that's used in the probability of weather type. Because of the vertical motion vertical levels that are available in AWIPS2 and the GFE, we can only calculate these prob ice present grids for the NAM, RAP, and GFS. But they are smart initialized and can be viewed within the GFE. As a forecaster, here's one diagnostic I like to use. In this case, in the upper left, we're looking at the RAP -10 to -13 Celsius relative humidity. So we're looking at that layer where our probabilities are increasing from about 50 to 80% of having ice initialized or initiated within a saturated layer. With the water vapor loop in the upper right, in the initial hours, you can see the dry punch for this cyclone heading towards the Great Lakes coming in from the southwest. The dry punch is really well seen in the RAP -10 to -13 relative humidity here as values less than 30% streaming in from the southwest with that dry punch. What this allows you to do is get some idea on the plan view relationship or areal extent of that probability of ice coming in or decreasing from the southwest. I would also add that using it for the RAP, the NAM, in the GFS, in AWIPS2 is probably your best bet because it has the most vertical resolution from the models off of the SBN. So after we go through the ice producing layer, the next layer we want to look at is the warm layer. Here it's just depicted in yellow, this large bulging warm layer over 0 Celsius. So here our maximum warm layer temperature is nearly 10 Celsius. Many people have seen this Robert et al. Diagram from this 2000 work showing the depth of the warm layer versus the maximum warm layer temperature and the correlation coefficient around 0.8. So there seems to be a fairly strong relationship between how deep that warm layer is and what the maximum temperature in that warm layer is. So here's an example of the maximum warm layer temperature aloft here, like we said, nearly 10 degrees Celsius. And you can see the depth here of when it crosses a 0 degree isotherm is quite deep. And so this relationship that we're looking at with depth and maximum warm layer temperature is probably best visualized by a situation where we take that warm layer and we diminish the warm layer maximum temperature and we also diminish the depth. So notice the red depth here along the 0 degree isotherm is quite a bit less than the yellow layer. So this is that magic triangle, if you will, that linear relationship that is seen in a number of cases east of the continental divide, especially between the warm layer depth and the maximum warm layer temperature. That's why the top-down approach uses the maximum warm layer temperature as a proxy for the depth because of this tight relationship. Burgoyne also assessed the positive area in joules per kilogram of that warm layer. He basically looked at the yellow area here and calculated the joules per kilogram that were in that warm layer. And there's a very close relationship actually between the maximum T aloft and the positive energy within the warm layer. If we look at the diagnostic from Rauber's data set for positive energy aloft, and you see all those points plotted here, the linear line here gives us our R-squared value of 0.8744. Basically that tells us that 87% of the variability in the positive energy aloft can be explained by using the maximum temperature aloft. So there's a close relationship between the two. Further, let's look at the warm layer temperatures aloft for freezing rain cases. Here's just a simple box and whiskers diagram representing 20% on the left-hand side here, representing 20% at the lower part of the can and 80% at the top. You see 80% of these cases above the 20% here have a warm layer maximum temperature of over 3.1. That's 124 freezing rain cases from Rauber's work. Andy Just has 93 independent cases. While the box and whiskers isn't exactly the same, it starts at 25%, you see very similar numbers here. 75% of the population has warm layer maximum temperatures at 2.9 degrees Celsius or above for freezing rain. When we move over to ice pellets, you see a very similar situation in the box and whiskers diagrams. While there's only 18 cases, because ice pellet cases are much more rare, you see that warm layer temperatures are fairly similar to the freezing rain temperatures, basically telling us to get a full melt on your hydrometeor, if you have ice coming into the warm layer, you're going to need temperatures over 3 degrees Celsius. So this again is a full melt scenario where your ice from your ice producing layer would come into the warm layer, fully melt, and then freeze near the surface. And we'll talk about that a little bit later. So comparing those two cases directly, freezing rain's on the left and ice pellets are on the right, you can see those similar temperature regimes with 75 to 80% of the warm layer temperatures warmer than 3 Celsius for full melt and a liquid hydrometeor heading into the surface cold layer. What about the ice pellet cases that have a different look? Here are the ice pellet cases for incomplete melting. Basically, the ice hydrometeor comes into the warm layer, doesn't have a warm enough and deep enough warm layer to melt completely, and so you have some ice fraction left within that hydrometeor, which then quickly freezes, falling into a surface-based cold layer below freezing. In those cases, you see the spectrum is quite a bit different. 1.6 degrees Celsius and to 3.4 degrees Celsius is the main 50% of the population. So we're talking about a population that's centered between 1 and roughly 3 degrees Celsius. These probabilities and the ones we've talked about so far for the warm layer complete melting are used in the probability of weather type. So here's how the probability of weather type was used. we look at the maximum temperature aloft, and solely looking at the maximum temperature aloft, we diagnose a few different precipitation types. When the warm layer maximum temperatures aloft are cool, we see snow because the hydrometeor is obviously not melting. So as warm layer maximum temperature increases, we dramatically drop off the snow curve. As we move into warmer temperatures, basically between about 1 and 3 Celsius, we increase the sleet probability to near 100% between 2 and 3 degrees Celsius. This would represent the case where you have incomplete melting of the hydrometeor, and then the hydrometeor falls into a surface cold layer again to refreeze. Then, if we continue to warm our maximum warm layer temperature aloft, we get a full melt to the hydrometeor, and therefore liquid is diagnosed for those temperatures that are warmer than 3 Celsius. And you can see once we get to 4 Celsius, almost 100% probability there's almost 100% probability in taking that hydrometeor and completely melting it. One of the changes we did make this year to the probability of weather type was changing the maximum temperature aloft over to the maximum wet bulb temperature aloft. We did this to actually have better use of the probability of weather type in the western part of the United States where dry air has more of an impact. So we don't think there'll be, when we looked at the sensitivity studies, we don't think there'll be much impact at all east of the Continental Divide because most of the situations and precipitation type events there are fully saturated. So the wet bulb and temperature are fairly close together. But in the western US, we think it can have more of an impact at getting these forecasts right. So finally, if we just summarize the warm layer temperature aloft and what kind of an outcome we would get with ice introduced into that warm layer, when warm layer temperatures are below 1 Celsius, you have a high probability of snow. But as you increase that 1 Celsius maximum warm layer or wet bulb temperature, maximum wet bulb temperature aloft, toward 3 Celsius, you start to melt your ice hydrometeor more and more, and you start to become closer to an ice pellet forecast. As we further increase that maximum wet bulb temperature aloft above 3 Celsius, most ice hydrometeors that come into that warm layer are going to be fully melted, and then we'll have to diagnose either a freezing rain or ice pellet scenario. Important to note, when you don't have any ice introduced into the warm layer doesn't really matter because it's not changing the hydrometeor state. So there's no reason to assess the warm layer aloft if you never have ice falling into it. In that case, your situation is going to be a liquid outcome no matter how you slice the atmosphere up. So let's investigate these cases with the fully melted hydrometeor moving into a surface cold layer where the maximum wet bulb temperature aloft is warmer than 3 Celsius. These freezing rain or ice pellet cases are interesting to investigate. So let's look at the ice pellet cases and look at the surface cold layer. And what we're looking at now is that layer where the thermodynamics, again, drop below freezing right near the surface. When you look at the Rauber cases, and there's only 21 cases that were pure refreezing cases to ice pellets, you can see the layout here that the colder and deeper that surface cold layer, the higher probability you had of getting ice pellets to a full refreeze of that hydrometeor to ice pellets as it moved into that surface cold layer. So let's look at some of Andy's cases. He had 18 cases where the refreeze to ice pellets occurred after a full melted hydrometeor came into the cold layer. And you can see very similar results to the Rauber data. 75% of the cases had a cold layer depth of over 2,000 feet. And 75% of the cases also had the minimum temperature in that cold layer colder than -6 Celsius. So you really start to increase your probabilities once you get colder and deeper, especially deeper than about 2,000 to 2,500 and colder than -6 Celsius. So relating it back to the probability of weather type, the probability of weather type uses a probability of refreeze sleet grid. And it only looks for wet bulb when your max TW aloft is greater to or equal to 3 Celsius. So this assumes that you have a full melt coming in from aloft of that hydrometeor, and then the surface cold layer is checked to make sure it's 2,500 feet deep, And then it uses a probability curve that you see here. And as temperature gets colder and colder, you start to get a higher probability of refreeze to sleet. So that's strictly based on the minimum temperature aloft in that surface cold layer. So Blake Burgoyne looked at the positive energy aloft for the warm layer. He also looked at the negative area to the surface cold layer, and that would be depicted here in the yellow area that you see. So we looked at the relationship simply between that negative low-level energy and the probability of refreeze to sleet. And they're two different techniques, and you can see that the relationship, while it's not too bad, 0.83, it's certainly not as strong of a relationship as we saw with the warm layer aloft. But there certainly is a relationship between the negative low-level energy, if you did an aerial calculation in joules per kilogram, and the probability of refreeze to sleet that's used in the probability of weather type. So there is a footprint of Burgoyne that is alive in the probability of weather type. One other operational note to add, ice pellets are pretty rare to get all on their own. They tend to reside in parameter space that has other types associated with it. So the thermodynamics, because it's in that 1 to 3 range Celsius of max temperature aloft, and then also found at ranges that are warmer than 3 Celsius, you tend to get ice pellets that are typically mixed with other precipitation types. Cortina's published a paper in 2004 that just looked at surface observations. And so only 30% of the time are ice pellets observed on their own. They're mainly mixed with snow, and they're also mixed with other types that you see here. So forecasting just ice pellets is a fairly rare occurrence. So our final stop on the top-down tour takes us to the surface cold layer. Now, we've already talked a little bit about the surface cold layer in its relation to refreezing ice pellets after a full melt to the hydrometeor in the warm layer. Let's talk about a couple other situations. What if we have ice incoming? Will the situation, which typically looks like this, will the low-level thermodynamics be able to melt the hydrometeor as it approaches the surface? Typically, the wet bulb temperature can be used for this, and if you look for wet bulb temperatures of greater than 1 Celsius for about 1,000 feet, it will likely melt the ice, and then you'd expect rain. And so as your freezing level decreases, you can expect more of a rain-snow mix and possibly even just snow, depending on how cold or how low that freezing level is. Another scenario is you can have liquid incoming from above, and we've talked a little bit about that scenario. We've talked about the ice pellet scenario where the colder and deeper your surface layer, cold layer is, the more likely you are to get ice pellets. But there's also a situation where you can have liquid incoming, and you have to check out if you can either produce freezing rain or rain, depending on what your low-level thermodynamics look like. I think traditionally the forecaster has always looked for freezing rain scenarios to be at 32 degrees for the ambient temperature or above. So basically if you're freezing or not freezing determines freezing rain. But with the freezing rain model, accumulation model research by Sanders and Bargenbroek, I think it's important to recognize that there's more to it than just looking at the ambient temperature in the low levels. Wind speed and wet bulb temperature play an important role. Finally, you can always have ice nucleation occurring in your surface layer. So it's important to think about having a surface layer that's saturated and what your minimum temperature is within that layer, because you could activate ice nuclei within that layer and start to snow when you might have thought you were in a freezing drizzle environment. Finally, let me share some other nuggets of information with precipitation type forecasting. Some things that we need to be aware of. First, dry layers. In the dry layer scenario, we need to make sure that the cedar feeder mechanism is not going to be kicked in, or that our ice that we diagnosed in the ice producing layer is going to fully sublime. So one of the things in looking at the research is that relative humidity layers of, say, about 75% or less, it looks like the furthest a hydrometeor can make it is about 5,000 feet. So early on in this forecast, or in this lapse sounding analysis loop, you see that the dry layer is indeed over 5,000 feet deep. Therefore, we wouldn't expect the ice that's forming in the saturated layer in very cold temperatures aloft to be able to move through this layer and interact with the saturated layer that's near the surface. One of the good things is the probability of weather type does actually analyze for the Cedar feeder mechanism. And the Cedar feeder mechanism is when ice is introduced from a layer above into a supercooled liquid layer, it actually glaciates that layer into ice. And so the probability of weather type will check for that, and it does it when it looks at the prob ice present grid and calculates the probability of ice present. So we've already talked about that grid once, but here's how it relates to the Cedar feeder. If there's a dry layer of 5,000 feet, it will not allow ice to make it vertically into that supercooled liquid below, liquid layer below. So the probability of weather type will scan vertically for dry layers of 5,000 feet. And then if it does scan that layer and find a 5,000 foot layer where the relative humidity over ice with respect to ice is less than 75%, it will take that ice and act like it's sublimed and not have it in the environment in the probability of weather type. So in this scenario here, the probability of weather type would analyze the situation very similar to what you would as a human. It's seeing that the layer is shrinking, and so basically you start at the probability of ice at the beginning of the loop with 0, but for this grid point, you then go to 100% chance of ice as the entire sounding saturates. This is a great case, and we're going to look at this a little bit more on radar. So this is a lapse sounding over the La Crosse forecast area. Let's look at what happened on the radar for this case. In the upper left, I have clear air reflectivity. We are in VCP 31 to get the most sensitivity for this case. Point C represents the sounding environment that I just showed you from lapse. In the lower right, I have the correlation coefficient. One of the things you notice early on in this loop is that the reflectivity starts to increase rapidly. This is a 3-hour loop. So the reflectivity starts to increase, and as it does, you look at the correlation coefficient, and it's in this hot pink zone to begin with. So let's look at that loop again, hot pink. So what we had is ground observed freezing drizzle in this area near C. So basically, the Cedar feeder was not activating. However, by the end of the loop, we had a higher level cloud deck move over the top, and as you saw in the lapse sounding, that ice environment eventually saturated down and seeded the freezing drizzle or the supercooled liquid layer that was near the surface. And so you see that actually taking place with the reflectivities increasing rapidly here within a few volume scans over to the red reflectivities, which were somewhere near 20 dBz's. And then down below in the correlation coefficient, you see a nice match with all of the correlation coefficients lighting up in red, where the precipitation type was changed over to ice or snow. Let's talk about one other area, and that is drizzle and freezing drizzle. This is just a loop of observed drizzle or freezing drizzle cases. And we're going to just loop through this a little bit, and what do you notice? You notice a fairly similar look to many of these soundings. They have a low-level saturated layer, typically involve an inversion, and then a very dry layer aloft. So when you look at freezing drizzle situations and look at the ingredients that are involved, first, it's dominated by a warm cloud collision coalescence process. So we're looking at upscaling cloud droplets into droplets that are large enough to fall as precipitation. And so that has to happen in the warm cloud at temperatures that are warmer than minus 10 degrees Celsius. So we're looking for those layers that don't have ice introduced. Typically, drizzle and freezing drizzle that is not a tropospheric deep saturated layer that's occurring there. Obviously, as you saw from the loops, these saturated layers are ground-based. So there's a couple things here. As we increase that layer depth, we're increasing the probability for precipitation. And why is that? Simply because the deeper the layer, the more cloud water that is available to be changed into precipitation through collision and coalescence. So the increasing layer depth leads to a higher probability for precipitation. Generally, looking at the research and modeling studies, about 1 kilometer is a good minimum depth for a saturated layer to produce precipitation. Second, or third on the list, but second to the precipitation process, is obviously you need a vertical motion source. So you need prolonged vertical motion within the saturated layer to have those drops grow from cloud droplets to the size of precipitation particles, precipitation drops that'll eventually start to fall and have a fall velocity that's fast enough to get them to the surface. So when you boil it all down, drizzle and freezing drizzle, the more water you have in that saturated layer and the more lift, the better it is to produce precipitation. Here's a loop, an IR infrared loop over the Midwest and Great Lakes with a case from 2007 where there was a cyclone moving from southwest to northeast, not too uncommon for December. And the clouds here are colored by cloud top temperature. And so what you see in the grays here are the cloud top temperatures warmer than -8 Celsius. So a very low probability that ice would be in these clouds below. And so the loop starts here in these more flamboyant colors, which are ice. So some of the snowfall moved off to the east, the accumulating snow. And then the area was left, at least my forecast area, was left in this very gray area of cloud top temperatures warmer than -8 Celsius. And so what we ended up doing ahead of this low, which provides the lifting, also in a little bit of a warm advection pattern there. Between that and the convergence of the low, we ended up getting about 3 hours of freezing drizzle and 1/10 of an inch of glaze ice. But pretty predictable if you look upstream and know what's coming at you. Finally, let's just talk a little bit about isothermal layers, which is a little bit of the probability of weather type limitation. Remember, the probability of weather type was founded on the idea of maximum warmth aloft probabilities being diagnosed without a relationship to depth. So again, here we're looking at the maximum warm layer temperature and the depth being proportional. But what happens when you have a situation like this, where the maximum warm layer temperature is not that nice triangle that you typically see east of the continental divide, but more of an isothermal layer? What we typically expect to see is more of a triangle there to the thermodynamic profile for the maximum warm layer. So what happens is your maximum warm layer temperature is diagnosed much cooler than you'd expect, but you have a very deep layer above zero that's going to melt the hydrometeor. So in this case, when you look at the probability of type probabilities that we diagnose from the maximum warm layer wet bulb or temperature aloft, in this case scenario, you get something that would be more in the sleet range rather than full melting and the liquid range. So something to be aware of, that these environments where you have an isothermal profile, that you might get more melting and end up with a precipitation type that's slightly warmer from a different hydrometeor change of state aloft. What is kind of interesting too is that the Burgoyne technique, here's just a buff kit example relating it back to operations. If we just look at this layer down below here, if we go into buff kit, we can look at the precipitation type that would be diagnosed within the Burgoyne technique by clicking on the precipitation type, and then you see the positive area and negative area on the left-hand side matched up, and that this sounding falls in a freezing rain scenario. So it's assessing the positive area that you see within this sounding. And by clicking on the lower left, the Burgoyne precipitation type, that's the active type that you see in the lower left-hand side of this sounding. The one curious thing, however, though, and one of the limitations of the Burgoyne technique, is it doesn't look for ice introduction into the warm layer. And you can see in that -10 to -20 degree range that saturation is quite questionable in this case. And you might actually end up with a deep liquid layer here that has no ice being introduced whatsoever. And that would be a great situation for a freezing drizzle situation. And because it's so deep and you have so much liquid available to it, it might actually be large droplets and actually be more of a freezing rain scenario just based on the depth of this layer being nearly 2.5 to 3 kilometers. So that's the whirlwind tour of the precipitation type top-down approach and its relation a little bit to the probability of weather type. Thanks for your time today, and if you have any questions or you're looking for any references, just drop me an email.